99% of all global internet data travels through a network of fragile glass tubes resting on the dark, freezing floor of the abyss. Satellites aren't keeping us connected. It's a physical industrial web of over 500 cables stretching across 930,000 miles in the deep ocean. These cables are barely width of a standard garden hose. Yet they carry up to 250 terabits of data per second at the speed of light, all while enduring ambient pressures exceeding 10,000 psi. But the real engineering miracle isn't just the cable itself, it's the extreme logistics of laying them perfectly across underwater mountain ranges, and the brutal reality of hunting down a severed line in the pitch black, dragging it 20,000 feet to the surface, and splicing a microscopic glass thread by hand inside a swaying clean room. In this video, we are going inside the extreme maritime engineering keeping our digital world alive and looking at the physical points of failure that could shut the global economy in blink of an eye. To understand how this global network survives, we have to slice that 17 mm cable wide open. At the dead center is the core. Usually contains between 16 to 24 individual strands of ultra-pure silica glass. Each strand is thinner than a human hair. All of your network data, bank transfers, and messages travels through these fibers as rapidly pulsing lasers. By using a physics principle called total internal reflection, the light bounces off inside of the glass at 124,000 miles per second. But glass under 10,000 psi of water pressure could instantly crush into dust. So, the rest of the cable is purely dedicated to armor. The glass is packed inside a polycarbonate tube filled with water-blocking gel, covered by a thick copper tube. Next comes the physical skeleton. Tightly bound galvanized steel wires that prevent the cable from snapping under tension. Finally, the whole thing is baked inside a layer of high-density polyethylene to save it from corrosion caused by salt water. That is what a deep ocean cable looks like. But there is a fatal flaw in relying on light to transmit data. Even in ultra-pure glass, light doesn't travel forever. The laser pulse starts to dim due to scattering. If you shoot a laser from New York to London, the signal will fade to absolute zero before it even reaches halfway. To fix this, engineers drop optical repeaters into ocean every 50 miles. When a dying laser enters the repeater, it hits a special section of fiber infused with rare earth element called erbium. A secondary pump laser blasts the erbium, instantly multiplying the light photons. It takes a dying signal and blasts it back to full strength. But these lasers need electricity. Remember the thick copper tube wrapping the glass core? The only reason high voltage electricity is running across the ocean floor is to power these amplifiers, so your data doesn't die in the dark. But how do you actually put thousands of miles of rigid cables at the bottom of the Atlantic? The answer is colossal specialized ships carrying entire transcontinental cables spooled inside massive circular tanks. They move at an agonizing crawl, often just 1 mile per hour, feeding the line into the water. On the floor near the coast, underwater robotic plows dig a trench in the seabed and bury the cable. They do this to hide it from our massive machines. The media loves the cinematic idea of sharks and deep-sea monsters chewing the internet cables, causing the internet to stop. But the truth is, marine life accounts for less than 0.5% of all cable damage. Commercial fishing trawlers and dragging ship anchors are responsible for over 70% of all cable cuts. And the remaining percentage of the cable cuts is done by several factors including natural hazards. Out in the deep ocean, the cable simply rests exposed on the silt. Out there, the ultimate engineering nightmare is the Earth itself. Tectonic plate shifts and underwater avalanches can snap a heavily armored cable in a microsecond. When an earthquake severs a cable, how do you find the break across 930,000 miles of pitch black ocean? You use the speed of light against it. Engineers use an instrument called optical time domain reflectometer. They fire a specialized pulse of light down the broken glass. When that light hits the severed end of the cable, it reflects back, creating an optical echo. Because they know the exact speed that light travels through this silica glass, they simply clock the time it takes for the echo to return. Multiplying it by speed gives them the exact coordinates of the break. A repair ship sails to those coordinates and drops a grapnel hook up to 20,000 feet down into the dark. It drags the ocean floor, hooks the dead cable, and pulls the severed end to the surface. There, to repair it, technicians cut away the damaged section and splice a brand new segment of spare cable to bridge the gap. Looking through a microscope, they fuse the glass back together one hair at a time. This means the repaired cable is now significantly longer than it was before. They cannot simply throw it overboard, because if they do so, the extra slack would coil upon itself, kink, and instantly snap the glass again. The ship must carefully lower the newly joined section back into the water. They move perpendicular to the original path, laying the excess cable down in a massive U shape so it rests perfectly flat on the ocean floor. Once the grid powers back up and the 10,000 volts push the lasers back to life, the ship sails away. But how powerful of an engine do you actually need to drag these massive cables from the bottom of the ocean? Next up, we are going to break down one of the most powerful ship engines in the modern world. Subscribe to the channel so you don't miss out.